everybody. We are going to continue with the classes of our course in Extractive Metallurgy. Today we have the class number 6, and today we are going to talk about the mass balances. This is a very important topic because it's the way to learn about how is a process in a furnace, in a reactor, in a pyrometallurgical process or a hydrometallurgical process. The idea is to define, to understand how is working process in a chemical, in a chemical reaction in a factory in order to define how much produce, how much product we produce, how is the balance between the raw materials who enter to the reaction, and how are the contribution of the products and the relationship between the product and the wastes. And of course, we have to define how is the material, how is the quantity of material, how is produced during the reaction. And this is very important in order to define the efficiency of the reaction. At the same time, it's important to determine the characteristics of the wastes, the gases, the liquids, the water, and of course the product. This is a key topic in order to define or determine the environmental topics when you are working in a metallurgical process. Today, in this class, we are going to work with the pyrometallurgical process. And in the next class, we are working with a hydrometallurgical process. Okay, in order to work, we have to define the characteristics we have to define the characteristics of the reaction in a reaction of the high temperature. This is very important to determine uh, how we are working, how is the condition of the material we are defining, how is the condition of the material. In biometallurgical processing, is very important to define the raw materials and the gases. Of course, the most important gas that we are going to work is the air. In this course, in order to work, we are going to consider that the air is 79% of nitrogen and 21% of oxygen in volume. Okay, this is our definition. It means that maybe we have another components of the air, but in this course, for this purpose, we are going to work with nitrogen 79% and hydrogen in oxygen 21%. Okay, in volume. It's important to define that. Another point that is important to define is to determine the stoichiometry of the reaction. We are going to define a reaction, chemical reaction, and we are going to define the reactor, the reactants, and the products of the reaction. And we have to define the stoichiometry of the reaction. It's very important. It's a key process to define the stoichiometry of the reaction. Is very important. And another consideration is that in a furnace, we are going in a pyrometallurgical process. We are going to work in a furnace. Be clear of this. All the raw materials, all the reacts to enter to the furnace don't stay in the furnace. All the materials enter to the furnace and returns or leave of the furnace. It's important to find that. It's important to be clear. In the furnace, you don't have material. The reaction is in the furnace. Inside the furnace is the reaction. But after the reaction, the products are outside of the furnace. You don't have accumulation inside the furnace. It's important to define. Okay. In a pyrometallurgical process, it's important to work, of course, we are going to work with solid materials and with gases. It's a heterogeneous reaction. We in metallurgical processing, especially in pyrometallurgy, we are working with heterogeneous reactions. and it's a key word. It's a key. We have to define that. Okay. It's important to define always we are working with a when we are working in a exercise like this, we have to define a base, a special base of calculus. Okay, it's a quantity, is an amount of raw materials in order to work. And the base of material, the base of material is really the key raw material or the material that is the limited reactant is the reactant ends easy. Maybe we are working with a sulfide in a roasting process in presence of oxygen. The oxygen is contained from the air, or the limited reactant is the sulfide. Okay, is the material that finish first, and it's important to define the quantity of that raw material we have in the product. It's a key process. Okay, it's important to define that things. When we are working with air, it's important to define. We have to define the density of the density of the air, or the and of course the molecular weight of the air. Which is the molecular weight of the air? We have to define the composition of the air and the molecular weight of the components. We have the component. The one component is nitrogen, and another component is oxygen. And we have to define the molecular weight of the air. For us, the molecular weight of the air is 28.8 grams or more. Okay, this is the first characteristics, because the nitrogen is a gas that the molecular weight of the nitrogen is 14 grams or more, and the molecular weight of oxygen is 16 molecular weight. And it's a double molecule. We have nitrogen is N2, and the same with the oxygen. The oxygen is O2. Okay, it's important to define that. And when we are going to work with gases, we have to define the characteristics of the gas. Okay. The other important thing is the density of the air. The density is important to compare with the water. The density of the water is 1 gram per cubic centimeter. Okay, or 1 gram or milliliter. And the density of the air is 750 less than water. And we said that the density of the water is 1 gram per cubic centimeter. The density of the air is 1 divided by 750. 750. This is the density of the air, and it's important to define that. Okay, in order to know the characteristics of the material. And the idea is we could consider the air as an ideal gas. It's important that we are going to work with the ideal gases law. In this is the ideal gases law is a equation, fundamental equation, and it's an equation that relates the properties of the gases. In this case, pressure, volume, number of moles, the constants of the gases, and the temperature. Always the temperature is in Kelvin grades. Okay, it's important to define that. For the pressure, we could use different units. The common unit is atmospheres, but we could work with bars, kilobars, and another different options, another different possibilities. In Anglo-Saxon countries, it's common use PSI. Okay, it's important to define the units the different properties. Volume, we could use liters, we could use milliliters. Also, we could use cubic meters. This is another possibility to find the, the volume. And about the units of the constant of the gases, we could use uh, atmospheres per liter divided Kelvin per mole. Okay, this is very common. And then the value of the constant is or 0.0082. Okay, this is one of the values of the constants. Or you can use another constant, another units. For instance, atmospheres per liter is the same that energy units as calories, and of course, joules. You can use different options. If you are going to use calories, you have to use 1.987. Okay, this is the units for the in gas constant using calories. Okay, and you can use also joules. If you are going to use joules divided by Kelvin mole, you have to use 8.314 for the constant of the gases. Okay, this is important to define. Okay, think about a special exercise, a special metallurgical problem when you are going to use a special transformation in the furnace. Okay, I have an example here. The example is try to transform a sulfide in presence of air using high temperature. This process is known as roasting. The roasting is the transformation of a sulfide in order to obtain an oxide. Okay, you put the sulfide in presence of oxygen, increase the temperature, and you obtain an oxide and another gases, maybe SO2. SO2, the oxide of sulfur. This is a very typical reaction in order to transform sulfides in oxides, and then you can transform the oxides, maybe a reduction of the oxides in order to finish the metallurgical problem. But here in this example, the idea is to transform sphalerite, a concentrate of sphalerite, and in this process, the idea is to transform 100 kilograms of sphalerite that is in terms of real process is not exactly sphalerite. Sphalerite maybe is only sulfide of zinc, but it's very common that the sulfide of zinc is have the presence of another metals as iron or maybe silicon. Iron is present. The presence of iron is common as a pyrite. Maybe it could be as a pyrometallurgy, but the most common product is pyrite. Okay, in this process, in this particular case, we have a concentrate that the composition of the concentrate is 50% of zinc, 13% of iron, 32% of sulfur, and 5% of silicon. In the theoretical way, this concentrate could have only sulfur and zinc. But as I explained to you, is common the presence of another sulfides, in this case aspartate. Okay, in this process, we are going to obtain after as a result of the process a product that has the composition that we have here in the example. We are in the raw material in the sulfides that enter to the furnace. We have 50% of the zinc, but at the end, when we finish the roasting process, we have 54.5% of zinc. We have 14.1% of iron and 5.4% of sulfur, and another constant, another composition of the silicon. Which is the case? Which is the condition of this process? We are going to change the sulfur, the sulfide for an oxide. Okay, and we are going in this problem. We are going to define the quantity we have to define. In the problem, we said we have 100 kilograms of raw material, the sulfides. We are going to obtain 85% or 85 kilograms of product, or solid product. But at the same time, we are going to obtain dust. Okay, and we have to define how much of dust we are going to obtain in this problem. We are going to obtain 8% of XO2 in the gases in the chimney. Okay, and we have to define the characteristics of the product in the chimney. Okay, which are the characteristics and the composition of the gases. We have to define the air, the total air that we use in the reactions, and the characteristics of the reaction, the final reactions. This is the problem we are going to solve now in order to understand how is the condition of this form. Okay, let's go to take the point. Okay.
Okay, let's solve this problem about roasting process. We have here furnace. This furnace have a reaction. We have the concentrate here. He says this is the sulfide, and we have the concentrate. We have 100 kilograms. Also, we have air. The composition of air is nitrogen and oxygen, 79% and 21%. Here we have a reaction, and as a consequence, we have a product, the roasted process. This is the roasted. The roasted is 85 kilograms. Sorry, kilograms. No, 85 kilograms. Also, we have dust, and as a result, we have gases. Okay, and the problem says that we have to define the quantity of gases. We had to define the quantity of dust, and we had to define the quantity of air. There are the questions in this problem, this exercise. The exercise says that the composition of the roasted problem and the dust are the same. They have the same composition. The other is we have mm, we have now the the concentrate is 50% of zinc, 13% of iron, 32% of sulfur, and 5% of silicon. And as a result, we have the roasted product, sorry, has 54.5% of zinc, 14.1% of iron, 2.7% of sulfur, 5.4% of silicon, and the rest is oxygen. It's important to say that we are changing a sulfide for an oxide. This is the result of the roasting process. Okay, the first problem we have to solve is to define the quantity of gases. In this kind of exercises, we necessary to prepare a balance of mass balance, and in that sense, we could say that we are mass balance of zinc. This is the most important thing now. In that sense, we have to define that the concentrate for the percentage of zinc and the concentrate is equal to the toasted or the percentage of zinc in the roasted process mass plus dust, the percentage of zinc in the dust. If we replace the values, we could say 100 kilograms, 5% 50% is equal to kilograms of roasted process with the percentage of zinc plus the kilograms of dust, or the percentage of dust is the same. And here we have the equation to define the percentage of the kilograms of dust. The kilograms of dust is this. This is the solve we had to do. In that sense, solving the problem, the result is 6.7 kilograms. This is the mm, result of this problem in order to define the kilograms of dust. Okay, if we are going to define the kilograms, we have to define the gases that we have in the as a result of the reaction. For the gases, we had to prepare this reaction. The reaction is the the kilograms of those in order to define the composition of the gas. We say that the sulfur plus oxygen is the result is SO2. Okay, this is the 1 mole of sulfur reacts with 1 mole of oxygen in order to obtain 1 mole or 1 mole of SO2. Okay, this is the situation we have to solve this now. But where is the sulfur? We need to do a mass balance of sulfur. Okay, and we could say that. Okay, continue with that. We said that in the gases, the final of the gases, the total gases has 8% of SO2. Okay, this is the reaction we have to define now, and we need now to calculate the mass balance that we have in the process. Okay, this is the thing that we have to define in this problem. Okay, we have to establish the composition of the gases in this reaction. In the reaction, really, we says that where is the sulfur. We could say that in order to establish the balance, we said that the concentrate we are going to define here. The concentrate has percentage of sulfur. The roasted process has concentrate of sulfur. The dust has percentage of sulfur, and the gases has percentage of sulfur. Okay, Now we had to define this. We know that here is 100 kilograms of concentrate has the percentage of sulfur. The percentage of sulfur we can see here is 32%. It's 32%, and the obtain is the roast process is 80 kilograms, 85 kilograms, but the percentage of sulfur is, you can see here, 2.7%. It's the same quantity in the dust, 6.7. We calculate that. So 27, and the gases for the percentage of gases, percentage of sulfur in the gases. Have to define here. Have to define here, and we have to put here the gases, percentage sulfur in the gases. Okay. If we make the calculation here, the gases for the percentage of sulfur in the gases is 29.8 kilograms. Okay. If we define the number of moles, is the same of no, 931.25 moles of sulfur. Okay, this is the same of uh, in this equation. It means no 935 31.24 moles of XO2. Okay, and it represents 8% of the total. In this sense, it means that it's the same. Sorry, it's the same of um, 11,341 moles gases. Gases. It means 261 cubic meters of gases in total. Okay, this is the total of the gases. We could define this one. This is the answer of the second part of the problem. Okay, and the third question is about the air. Okay, we in order to define the quantity of air, we now to define the quantity of oxygen that we have in the furnace. Remember, we had the furnace, and in the furnace we have air. We have the interest of oxygen here, and we have oxygen in the process, in the dust, and of course in the gases. Okay, we have the furnace here, and we had to prepare the mass balance of the oxygen. Okay, this is the thing we had to define now in order to put the calculation here. Calculation here is to take the air. We have to say this is air. We need to know the percentage of oxygen is the total of oxygen, or the percentage of oxygen. This is the number we have here. This and we had to we have the same in the dust. mm, the same quantity, and here is the percentage of oxygen that we have in the gases. Okay, this is the activity, the calculation we have to do. If we replace the values here, we say that percentage O2 is 80 kilograms, 85 kilograms, or 0.233 plus 6.7, the same number, and the gases, the quantity of oxygen in the gases. We have to, this is the number we have here. If we make the calculations, we could say that the air, the percentage of oxygen there is the number we have here plus 1.6 plus the number we have here is this one, because the percentage of oxygen is the percentage of sulfur. It's kilograms. It means that the air oxygen is kilograms of oxygen. This is the value we have. If we change to moles, is moles of oxygen. This is the value we have to replace here. Okay, this is the total. Where is the total? Where is the material? This is the stoichiometrical oxygen that we react in the reaction, uh, and we know that this is the 21% of the total. It means that we have uh, 7,619 moles of air. Okay, this is the stoichiometrical. It means in stoichiometrical, and of course the 79% of this number is 5,543 moles of nitrogen. This is the stoichiometric. Okay, it means what it means. It means that the total we obtained in the last part, in the second part of this exercise, 11, this is the number, this is the number, 11,641 is the number of moles we have here. This is the number we have, plus 43, 5,093, this is the number of moles of plus air in excess. If we calculate that, it says that the air excess is 4,767 moles. Air excess is the same is 1,107 moles of oxygen in excess, and plus 3,765 93 moles of nitrogen. In total, for the chimney, the gases, complete the gases is SO2 plus nitrogen stoichiometric plus nitrogen in excess plus oxygen in excess. What is that? This is 932, 931 to 0.25 plus 5,943 plus this is 3,765.93 plus 1,007 moles. In total is if we make the total gases is different total is what it means 8% of SO2, 83%, 3.5% of nitrogen plus 8.6% of oxygen. This is SO2, this is nitrogen, and this is product excess. Okay, this is the final result. The final result of the problem. In this sense, this is the category of we are looking for, the answer we are looking for. And in this way, we finish the exercise. As an extra, in maybe a review, the problem we have concentrate sulfide, sphalerite, sulfide of zinc. Using a roasting process, we obtain an oxide. This is the final product, the roasted product. Roasted product is an oxide. We have also dust and we have also gases. In that sense, we make some mass balance. First, we made a mass balance of zinc. Then we made a mass balance of sulfur. And finally, we made a mass balance of oxygen in order to define the kilograms of gases we obtain by the chimney. We make the complete calculation of the problem. Okay, this is completely the material, and in this sense, we finished the exercise. Okay, thank you very much, and see you in the next class of this course. Bye bye.